All right. Good afternoon, everyone. Thank you for staying until the last session. I'm a professor in the Mechanical Engineering Department at MIT, and as a result of that position, I find it really interesting to have sort of one foot in academia, teaching and research, and one foot in the professional world, including as a co-founder of Desktop Metal. I'll start with why, in my view, I think a lot of us are here. And that's the idea that if we define manufacturing at large, I define manufacturing to my students in manufacturing at MIT as value at scale. So many things are manufactured, but typically we must manufacture them in such large quantities to make viable businesses. And moreover, if you look at a little bit of history and compare, say, a factory from 100 years ago to a factory of now, specifically an auto body shop, there's been a lot of change. But actually, I think there's a really, really big problem. And the problem is that while we've advanced in the technologies we use in design and manufacturing throughout, without a doubt, we've also created a lot more complexity. And the numbers on the bottom, just tend to make an interesting order of magnitude argument. Automobiles in 100 years have become much more capable, but they're also 10 times more complicated in terms of the number of parts, require 10 times the number of assembly steps, are made one every 1/10 of the time, and on an inflation-adjusted basis cost about 10 times the amount of money. And I'm not here to tell you about the intricacies of automotive design and manufacturing, but rather to make the point that while manufacturing is awesome, makes the world go round in some ways, if you step back and think about it, it's not only really hard, but is in some ways really inefficient. So perhaps why we're all here is because we see the opportunity to become much more efficient, flexible, versatile, on demand, at the point of use, whatever words you use in your specific context. And if I, however, may sit on the idea of the automobile as a manufactured artifact, an automobile and many other products are so complex and so important that there exist businesses for the purposes of taking them apart and analyzing them. So this is a successful business in the Detroit area called Monroe & Associates, well known in what they do, but their business is they do competitive teardown. So they buy one or a few of every car and they take them apart and they do the reverse analysis of how they were manufactured and what the costs are. And just think of the many levels of complexity that are created by having to use today's manufacturing techniques that are so awesome in their own right, but so limited now that we can see the digital opportunity. And of course, it's not just the resources required to manufacture the part and realize that capacity at scale, but it's the design and engineering and iteration process for the part and for the tool. And I don't need to explain to you that if you're making a tool to make a part, say a sheet metal part, the tooling, design, and proofing requires iteration. So much opportunity for efficiency improvement. And now we come to the idea of 3D printing, aka additive manufacturing, as an enabler of transformation. And of course, many of today's 3D printing technologies in terms of the basic process, the basic idea, have been around for a long time. They were not invented yesterday. I like being from MIT to show a picture of a 3D printed model of MIT's main building from nearly 30 years ago. My colleagues, Ellie Sachs and their teams were among the pioneers who had ideas to build objects digitally in 3D using the processes that are just coming to fruition today. And you can look at the additive manufacturing 3D printing industry in many ways, and you can say that it's about $10 billion, as reported by the Wohlers report recently, in materials and services and machines. But moreover, what's important is an industry with structure is emerging. We have great interaction and collaboration among the software companies, the materials companies, the printer manufacturers, and the establishment of production capability, right? Whether it is in-house in companies that want to vertically integrate or grow the capability in-house, or via service bureaus, whether you interact with them directly or you interact with them virtually. And we'll only see continued growth in all of these areas and interesting collaboration and partnership and competition. And that's sort of the nature of that free market that's going to continue to grow the industry at an appreciable rate for the far foreseeable future. And one can also look at the capabilities of all the different printers we have, if you will. This is a video I took from one of our online courses where I'm manipulating a dynamic chart that basically looks at all the spec sheets of all the 3D printers you can buy for plastics and metals of different types and plots the machine cost versus the build rate of the machine. And my point by showing you this chart is simply we have a lot of tools that we can use to do 3D printing that work with different material sets with different capabilities, and we now have data that we can start to use to build models of economics and productivity and so on and so forth. And so, for instance, if you look at the green dots being, for polymers, extrusion, FDM, FFF systems, and the brown dots being selective laser sintering systems, maybe terms you can see the trade-off between the cost of the equipment and the build rate, the rate at which the printer produces the part. And those are metrics that you can use to build analyses of what a business case might be. But moreover, I think it's not only important to say, well, how much money is the industry generating every year, but what is the lens through which we should view the impact of AM, of additive manufacturing? And in our courses at MIT and with industry, we've adopted the idea of viewing additive through the lens of the product life cycle. So think that every part that's designed, every product that is sold, arguably has a life cycle from the day of the first concept, the first idea, to the end of its life, when, say, the last one on the road is serviced and used. And so we can think of 3D printing being used all throughout that product life cycle, not only for prototyping, but increasingly for end-of-life service parts, being the example here from Daimler heavy trucks, under-hood parts for Unimog vehicles, a heavy-duty off-road vehicle designed to last decades. And the first one, maybe you've seen it before, is 3D printing plastic potato chip models by Frito-Lay. So the applications are diverse, and the point is that you can go from the beginning to the end of the product life cycle and you can find value. But what's really exciting to all of us is the production applications, right? And we cannot argue that additive manufacturing is yet a true mass production technique, at least not writ large, but there are more and more compelling applications where functional high-value parts are being produced using 3D printing at scale. And this reflects, in my opinion, if one did an analysis, I'm sure a far greater investment in technology adoption and integration than the measure of printers and materials and services sold on a yearly basis. So you have more and more valuable metal parts, from jet engine parts to components of rocket engines to even high-end home goods. You can buy an expensive faucet where the water goes up the spiral lattice. More and more medical products, metallic implants, where the real special deal is that the lattice structure on the surface of the implant improves patient outcomes and integration. That's the case of the hip implant, but applies to many others. Dental products, we heard about those earlier today. Even Chanel, you can go to a cosmetic store and you can buy a Chanel mascara with a 3D printed plastic brush and designed to help distribute the mascara better on the eyelashes. So we're realizing the integration of these technologies in a true production context, and we're only at the early stages. One of my favorite examples, which maybe you've seen before, is this part from BMW. Right? I have no affiliation with BMW, but I really think this is a beautiful example because it speaks, number one, to the fact that we're just scratching the surface of 3D printing's applications in the automotive industry, right? The automotive industry is vast, has huge scale demands and also a very tight cost demands. So I think automotive will bring 3D printing to the mainstream like no other industry, in my opinion, but also that it's a story of design for 3D printing, achieving a very unique, complex shape, and also manufacturability. If you study it a little bit or talk to them, you find it's maybe a, you could say it's a silly little part. I don't mean that negatively, but it's just a little roof bracket to open up the roof of a high-end roadster. It's not an engine part or a chassis part. But nevertheless, it has a serial number, right? So it is a real production part. And also, if you look at how it's manufactured, it's designed with manufacturing in mind. So because of the process that they used, which has requirements for support structures and has issues with thermal stress in the process, they had to design it such that it could basically be manufactured post-processing free. They make 300 or so on a build plate, and they snap them off. So it's a beautiful example of not just the computationally guided design to make this beautiful shape, but also the incorporation of manufacturing constraints, this sort of full spectrum knowledge that's necessary to realize a useful application. But saying that you can make an exotic geometry by 3D printing and make a production case, in that case for tens of thousands of parts, is only thinking of one of the vectors for value creation. And so let me give you a very simple thought experiment. The experiment is the following. Consider a block of metal about the size of a deck of playing cards, or you could say it's close enough to the size of your smartphone. And imagine creating different versions of that, all the same external size, but with greater complexity, i.e. more features from different orientations, all the way up to a part with a very complicated internal structure, something that would be ideal for 3D printing because, say, it's lighter weight. And think of the cost of making that part versus its complexity if you manufacture it a conventional way, take here machining, versus the cost of making it by 3D printing. And just look at the cost of a established laser-based metal 3D printing process. And what you see, perhaps not surprising, but I think really profound, is that the trend of cost versus complexity is completely the opposite. If I machine it, it costs me more to make the part more complex because I have to use more machine time and take more material away. Also, I waste more material if I take more away. But if I 3D print it, the cost goes down with complexity because I use less material and use less machine time. And here is just one example. The details are in the specific case if you applied it elsewhere, but just one example, one copy of this part, where if I have a very, very complex design, it's already competitive to make it by metal 3D printing versus machining. And think of how you can capture that trade-off in the applications that's of interest to you. Many other stories. Here's tooling from Sandvik, a large tooling manufacturer. You can purchase this. This is a high-speed milling tool for use in conventional manufacturing made by 3D printing. They put the Hart insert on the 3D printed part. It's lighter. It can spin faster. It all has internal cooling channels. So this idea of reducing manufacturing cost by leveraging complexity is not even thinking about value and performance. Or more sophisticated examples exist in system-level design, part consolidation. You've likely heard many examples throughout the day. This is one from Siemens that I particularly like because they clearly describe how they redesigned a burner for their industrial gas turbine. Right? Siemens is not in the business of doing 3D printing to make 3D printers or 3D printed parts, but in the business of using 3D printing as a design vector to increase the performance of industrial equipment. So they redesigned this burner to have a higher performance in the combustion process of the turbine engine, but they also were able to reduce the number of parts significantly, reduce the number of assembly steps, and reduce the lead time. Right? Organizationally, I think they're probably still in transition to how they run a project like this, but from a performance point of view, you can think not only of how does the part bring value, but back to the idea of manufacturing being so inefficient, how can you consolidate operations and take value there? So we've heard a lot today about the digital thread, the digital factory, et cetera. And I think that we might all agree that software will spin the digital thread. But I also feel that the machines are the cornerstones of what we will establish as the future digital factory. So I'm fortunate to be a member of the founding team of Desktop Metal, which you heard about this morning from Rick, and I think the Desktop Metal production system is a great example of the machines that will be the cornerstones of the future digital factory. Now, if you ask me if Desktop Metal's process will win over all others, I will say it's too early to tell, and that each 3D printing process will survive in its own right. But there are many important principles that the team here and in other advanced 3D printing companies are working on that allow us to realize fundamental principles of scalability. This one being the use of inkjet printing to bind powder together and let you build parts quickly. And that's just a short video clip of one of the production-ready machines operating in their lab in Burlington. I understand some of you are going to get to visit there tomorrow. The other point I'll make is it's not just the printer, but it's the supporting hardware. So, we can say that the printer itself is fast and can produce good quality components, but it's about thinking of how you design the whole system around the printer to create a production workflow that creates parts. And this is a case where the companies developing these technologies need to work very intimately with customers to figure out in specific contexts what is the best way that the whole system needs to operate. So I will not dive into the details of different elements, but suffice to say it's not just the printer, it's the supporting hardware, it's the handling of material, and so on. And it's really exciting to me, with great credit to the team at Desktop and all the small and large problems they're solving and inventions they're creating, that they're thinking at the system level beyond just the printer. And I think that's really, really critical. And parts coming out of the machine look like this, and start small but have fine detailed parts and make a whole variety of geometries and make them in large quantities in a short amount of time. Another thing that is exciting is technology to trace materials across the workflow. Create a digital thread of data from materials. So here's an example from LPW, a company in the UK that has a technology to basically create data from the tracing of metal powders through 3D printing processes. For each 3D printing process, for each material, the exposure of the powder to moisture, its mixing, its reuse, et cetera, is critical to establish quality control. And it's great to see technologies like this reach the marketplace, and it's another part of the digital thread. Another thing that excites me is machines that focus on particular corners of the manufacturing industry, the manufacturing market, that are of their own high value. So another company related is BMF, and they're a startup of one of my colleagues' research at MIT, and they're focusing on stereolithography with projectors, right? You could say, same general concept, but their focus is on high precision small parts, and they can make small components and make them in some ways more precisely and in some ways more cost effectively than micro-scale injection molding. So it's not just plastic parts overall, but it's focusing on the micro-injection molding market and thinking of how 3D printing could compete in design, compete in speed, compete in flexibility. And it's great to see there are, now these benchmark AM technologies being applied to specific corners of the manufacturing market, and that's an indication of the industry reaching maturity. I'm also a big fan of large-scale 3D printing, not only large numbers of parts and factory-style layouts, but also big parts. So you may or may not have seen the large-scale 3D printing work underway for many years at Oak Ridge National Lab and commercialized through several partners. This is a big extrusion printer, the size of more or less half of this hall, and over a period of days it's printing a tool for layup of a composite component for an aircraft. And when I first saw this, I thought it was just a little experiment, but you really see the cost and time savings and design flexibility brought by this. So we can think of 3D printing not just to print parts, but also to print tools for manufacturing, and not just to print small components, but to create large components. And one of their examples is a multi-piece layup tool for the composite wind turbine blade. And there are advantages to having a 3D printed tool for a composite wind turbine blade, in addition to being able to create the tool more quickly. And the last example I'll show is just one I saw in a corner of one booth at the Form Next exhibition in Germany last November, and I just really liked it because it kind of hit a little spot. And here you have a directed energy deposition machine, basically has a laser, shoots powder, can be used for repair, and it has some vision apparatus, and it's mobile. So it can be used to repair traditional mold tools, and you can bring the printer, if you will, to the tool rather than bringing the part to the printer. So there will be perhaps unexpected uses of these different technologies when they're adopted to specific contexts. And I think many of the small and large uses are probably beyond our imagination. So to summarize the examples that I showed, I think it's exciting that the industry overall is not just thinking about speed in making machines faster, but in addition to making machines faster, we're thinking truly about how to establish productivity, end-to-end productivity. We also have an increasing variety of of hardware that can operate from small to large scale, right? We've seen the impact of Formlabs and other companies making productive, reliable desktop printers on not only, prototyping and small-scale manufacturing, but also being the accessible tool so then you can go to an industrial scale when you're ready. I think there's a very important connection between the evolution of these technologies and the market and application focus, whether it be a specific printer or printing system designed to a particular industrial market, or the coevolution of the application stories, the really valuable uses that then feeds back on the technology development. And I think the end game is indeed the digital thread or the digital tapestry from design to finished part. But in many ways, it is the hardware, the machines that will be necessary to enable the digital thread and create the consistency and data-driven reproducibility and productivity that the industry needs. So I tell you a lot of things that, many of the statements today are hopefully very ambitious and forward-looking and motivating. I hope you leave today with enhanced motivation that the future is bright. But there are also a lot of barriers. And so, what is the barrier? I think arguably, if we froze all the technology development and just accepted what we have now, the biggest barrier would actually be knowledge and learning. And I use this busy chart from a recent paper to support the argument, right? The plain fact is that all of this is very difficult, and I think one of the greatest challenges getting from here to there, the present state to the state of uber digitization, is that knowledge in organizations and the knowledge required to truly optimize one of these new production workflows is fragmented and requires deep expertise in materials and design and quality control and so on. And this chart is meant to represent an existing metal 3D printing technology, because you have powder and you have destructive and non-destructive testing and you have simulation and design. But the back and forth between knowledge and experience and what the computational power can do for you, I think, is an issue that is not going to go away, no matter how far the artificial intelligence and the tools we have advance. So this brings me to something that I frankly think about a lot. And I'm primarily at a university, and MIT is one of many universities working in the area of advanced manufacturing. And I think that universities can play an important role in this era of more flexible manufacturing and flexible thinking in trying to accelerate what industry can do. So what we do at MIT is try to help accelerate the progress of the industry, mainly in three ways. And the first is learning. Not only do I teach on campus, which all professors do, and I think is one of the greatest, if not the greatest way we make impact, but over the past year or so, we've made a really strong effort to reach out and work with industry on additive manufacturing education. And this is largely in the form of an online course that we launched about a year ago and has now been taken by thousands of professionals and professionals from, I would say, at least 200 different companies around the world. And this is a course that combines video of myself and colleagues lecturing, interviews with experts, as well as examples shown in high detail with real stories of the business case and the performance benefit and so on, to try to really, the best that you can in a digital environment, teach you the ups and downs of additive and its integration in the product lifecycle as a whole. And for me, it's been one of the most useful experiences in learning about where a technology really can go and what the barriers are, and it's had a great feedback to my research and the other things that I do. And we've also begun to have in-person workshops, and we've developed a few tools that seek to accelerate the sort of free-form conversation you would have when you're exploring, say, 3D printing for a new application. One of those tools is a little card game. We have a deck of cards that basically graphically, with simple text, lays out different process constraints and choices and design variables like light weighting and customization and so on. And we have a series of activities that you can use to kind of break the ice, especially if you're new to thinking about 3D printing as a way to come up with new solutions at any point during the product life cycle. And then you get this in front of people, and you find out how they really want to use it, and you get feedback. And something that we've come to also begin doing in the context of the next generation of our online course is think about kind of skill profiling. What are the roles of designers, of manufacturing engineers as you think of using more digital technologies, 3D printing and others, and what are the different knowledge bases that these individuals will need to have, and how can we bring that into our curriculum? So that's been a really rewarding activity, and you can find out more about the course online. The other thing that I take license to do as a professor is do research, and this is stuff that not necessarily will ever become a product, but we like to identify things that maybe there'll be a few hits, and are certainly ideas that we feel are unique when it comes to what industry is working on now. So I show you a few examples from my research lab. The first one is the following. So for a couple years, we've been working on a new kind of printhead that is analogous to an inkjet printhead, but instead of printing liquid or polymer or a regular ink, it actually prints particles. And it does that by a special mechanism where you eject the particle using an electric field, and it allows you to place microscale particles, say from a few microns to a few hundred microns, with precision registry, and then you can do things like melt them so they form these half dome-shaped droplets or lines of metal. Far from a commercial process, but a new technology that we hope might have a space in the inaccessible zone of some of today's 3D printing processes. Another effort actually sponsored by a large consumer products company that went in an unexpected direction is thinking about manufacturing using cellulose-based materials. So cellulose is the world's most abundant natural polymer, and we ended up developing a kind of 3D printing process that takes nanocrystals of cellulose. Basically, you take trees and beat them up until you have their smallest molecular unit at the nanocrystal size, and you can create an ink for 3D printing, and you can then cure that ink into a cross-link material that ends up having fairly high hardness and fairly high toughness. So properties that begin to infringe upon the realm of metals. They're not metals, but they're not polymers, and they're somewhere in between. So we have some really interesting results by designing a new material for 3D printing based on a natural polymer that in a way show one specific example of the opportunity to design even new materials for 3D printing that complement what's already out there. And then we're also motivated by maybe the under-the-radar problems that are really important to get the current and next generation of 3D printers to work better. So our group at MIT, in combination with a really awesome group of computational scientists in Germany, have developed a tool set for modeling the flow of powders. Right? The spreading of powder, metal or plastic, different sizes, different materials, is really important to getting a consistent 3D printing outcome, though maybe it's just one little thing you think of. And we've developed a tool set based on a very sophisticated computational toolbox from the group in Germany to be able to basically, in the computer, model the spreading and other attributes of metal powders and look at key things like the effect of the adhesion between the particles, which becomes very important as you get to smaller particle sizes and expose the powders to different environment, and then simulate the spreading process, for instance. And the idea here is you can then take one of these simulated layers, and you could then simulate the 3D printing, the fusion of the metal, or you could simply look at this layer of powder in the computer, and you could spread a layer of powder in your machine, and you could determine to what extent they agree, and you could say correlate defects you measure from your printer to defects in the simulated powder layer, and try to develop in the long run better, you could say, computationally driven quality statistics. That's a mouthful, we're not even there, but you can see the potential of these advanced computational tools to advance all aspects of the process, and the fact that every little detail is important to get it right. And bringing this all together, we've recently launched a new center at MIT, a consortium of companies that we call the Center for Additive and Digital Advanced Production Technologies, called APT, and that's our website. And it comes from meeting many companies and everyone wanting to learn more about what we're doing in this area. And we have 4 pillars of activity: research, strategy, learning and building an ecosystem, and the ecosystem really starts here in Boston with many of the great organizations that are in attendance today. And we are proud to have 12 founding members. You can see their logos here and several more members in the hopper. And I would welcome you to get in touch with us if you're interested in what we're doing. It is a mix of the kinds of research that I showed you, the educational programs that I described, plus forming a community of members who come to MIT and have workshops with us and help to identify the trajectory of the digital technology and define problems that require shared solutions. So I'll wrap up in just a moment and say the following. If I look at all of the kinds of examples that are shared today, I bring myself back to this chart, which says the following. Right? I may define manufacturing now as creating value at scale, right, where scale is large numbers due to the fixed investment we have to make. But in the present and future state, we really are all thinking about manufacturing becoming more adaptive. So I adopt this chart from a publication a few years ago by Brett Connor, who's at Youngstown State now, and it basically says, think not just value at large numbers, but think where you are or where you want to be in the three-dimensional space of production volume, complexity, and customization. And imagine that with digitization, we can create products all throughout this, virtual three-dimensional space. We can still make stuff in huge quantities that is valuable, but we can also customize individually, we can mass customize, and we can take complexity from being, a challenging thing to being an enabling opportunity for value creation and also a simplicity of consolidation. And when we think about how fast is the technology going to grow and how big will the market be next year, we can make useful predictions. But moreover, to me, one of the most exciting open questions is, what are the scaling laws? You think of in the semiconductor industry, Moore's law saying for decades that the number of transistors on a chip would double every 2 years. And that held for a very, very long time, right? I wonder, is there an analogous law that governs digital manufacturing? Or moreover, how do we create sort of actionable models that let us prescribe and quantify value when it comes to these types of transformations? Like looking, simply, but this requires a lot of detail, at an engineering process and saying it's not just the final component, but it's valuing the consolidation of engineering effort to simplify the design, perhaps increase performance, and also grow operational flexibility downstream. And what's really exciting when we talk to many of our industry partners is not just that there's great interest in learning and investing and buying printers and partnering with materials companies and all that jazz, but more and more organizations are starting to think far enough in the future in a stage where they're kind of allowing themselves to wipe a clean slate, to say not this product generation or even the next one, but maybe the one after that. How do we need to restructure a part of our engineering team and invest in the capacity so we are ready when the technology is ready? So if I leave you with one thought, it's the thought to really force yourself to think at the system level. Right? I often get trapped in the capabilities of what we have today and making this a little bit faster, a little bit stronger, but think about the system level implications. Right? Think about design. What can we unlock by new designs, function-driven design rather than form constraints? What is the implication of the future manufacturing system, the digital factory, if you will? How can our engineering operations, our production operations, be made more simple, more efficient by the consolidation of effort and the consolidation of design? And also, I loosely use this kind of scary personal transporter as an example. Think of all the really really advanced technologies that we have at our fingertips that are not only improving the fun aspects of our life and space exploration and autonomous driving and so on, but also the technologies that are critical to energy efficiency and ubiquitous communication and medical devices and so on, and think of the idea of, in particular, 3D printing as a enabling technology to let us create new designs from a clean sheet. And that's when I think we will only really realize what our imaginations will fulfill in the future. So I'll close there. Thank you for your attention. That's my email. Feel free to get in touch. And if you have a question, I think we have just a few minutes left. Yes, I think there's a microphone coming around. If
one thing it seems like is that for the cost of additive manufacturing to come down to a place where it becomes more competitive for actual production, maybe there needs to be a bit of unlocking on the monopoly of the materials.
Sorry, say it again.
I'm wondering if for the cost of additive manufacturing to come down, it seems that there needs to be some unlocking of the material, or bringing down of the cost of the input materials. You know, if you buy a Haas CNC mill, you don't have to buy 6061 aluminum from Haas forever.
For sure.
And I'm wondering how you feel about the input materials to the different additive manufacturing technologies, and can they be more open source and come down in cost in a commoditization way?
Great point. So, how does the materials landscape and the materials supply chain, open versus closed, affect the rate of growth and the cost reduction in AM? I think we're seeing more and more cases where, especially for AM at scale, right, to go to production, you don't have to be in a position where you buy the powder from the company that makes the printer, right? You can go to the powder manufacturer if you're going to buy a lot of it, and you can figure out how to make a handshake there, right? There are cases where it makes sense, and there are cases where it doesn't make sense. That's a bit of a wavy answer, but what I mean is, true production will be achieved by partnership between the machine company and the materials company and the end user. And there will be materials aspects that are proprietary, right? Say, take, binder inks, for instance, that, maybe you have to buy that if you buy the printer, but the powder might be purchased from a third party. A further point I want to make, however, is that the data flow through the whole process is important, right? So for materials companies, it's becoming more interesting, right? Not only how do you, bring yourself into the market and sell more material for 3D printing, but how do you capture value from the ability to guarantee that that material works in a particular process. So I think we're going to see, all extents advance and some really interesting, partnerships and business models continue to grow.
So as the AM industry grows, the job force for AM grows as well. From your perspective, on the technical standpoint of things, where do you see some of the most important skill sets germinating? So what are some of the future or current skill sets that are going to be the most relevant and in demand for people in the technical aspect of things in AM?
Yeah, so the question is on skill sets for 3D printing?
Yes.
I think, not in priority order, but ability to use, the new design tools as fluently as the old design tools, right? Be able to do generative design, topology optimization, whatever you call it, in concert with CAD. To truly understanding the capabilities and limits of the additive technology, even having experience with desktop 3D printers and knowing, what works and doesn't work, so you confront manufacturing constraints in the design. 3, a creative mindset, so think about function, not just, form or constraint, but 4, an awareness of manufacturing technologies overall. Because 3D printing is one tool in the proverbial box, and it's not going to be the only answer. And even if I you want to use 3D printing as a primary production technique, I, more often than not, need to do post-processing and perhaps machining and assembly and so on. So what we're getting in knowing the capabilities and limits of 3D printing is how they fit into the overall space.
Hi. So, is it on? So I definitely agree that education seems to be like the way to, I guess, allow these technologies to reach their potential. I had a specific question about like the online and the in-person trainings that you had talked about. I'm guessing that they go through different additive manufacturing technologies. Do they also kind of discuss like analysis and qualification, I guess, methods for different materials?
Yeah, the short answer is yes. The long answer is we don't yet have a dedicated course in qualification and implementation, right? So I think there's, for certain industries, there's the, having the material and process become qualified. There's also the organizational implementation, but that's something we at MIT are working on over the next year.
Hi, so you talk a lot about the progression of the industry, but we've definitely seen some sort of hype bubble burst around like, hobbyist FDM printers. Do you kind of see regression in any other area of the industry?
Sorry, I didn't hear the first part.
You talk about progression, but do you see regression in any other area of the industry aside from like hobbyist FDM, like any other misplaced development?
Yeah, the question is, do I see regression? I don't think I see regression. I see healthy competition. If you say who's thriving and who's struggling to survive, right? I would make the personal argument that, overall, if we look 5 and 10 years in the future, right? Many of the names today are, not going to be around. Not many, but some of the names today are not going to be around, and there are other names that, we haven't heard yet. So I think it's more so understanding how your idea, your innovation fits in the context of the industry and the application. Right? So maybe the regression is the companies that either are too scatterbrained, trying to create an everything solution, or those that just don't see the market and understand who the customer is and what the customer is looking for. And as industry gets more aware of what the real value propositions are, I think it's all about connecting with who your customer would be. Whether you're say going to produce parts, or you're going to make machines, or you're going to make material. I think that's what it's all about, to maximize the probability that you will thrive and you will grow as an organization.
Hey, sorry. I've heard 30 years a couple times, and it makes me think about patents and expirations. And I was wondering what your opinion was on the law aspect of this, because there seems to be a struggle between proprietary and sharing.
Yeah. The question is about intellectual property. So the good thing is that a lot of the basic processes, right, that were patented, in their basic sense, like FDM, are now available for broad, use. But when you look at, for instance, a particular, new 3D printer, new derivative technology, there's so much advanced technology of which an important part of that is proprietary, is intellectual property that is owned by that company. So on the one hand, right, you have openness and being able to adopt different baseline processes and take them to derivative uses. And the other end, you have continued invention and protection of those inventions. I think that the idea not only of intellectual property related to aspects of 3D printers and other production tools, but also the idea of the intellectual property in the design of 3D printed objects or digitally manufactured objects, and the instructions to make those objects is going to be really important. I don't necessarily mean you would patent the recipe to 3D print something, but in some ways, especially in metal parts, like the capabilities we're still so far at the early stages. When you hear people talk about microstructure or composition or functional grading, like we're not even close to there yet. There's so much for us to do, but think of the instructions of how to do that being very, very special and being, you know, a point of value. And I think it's be really exciting to see how that shakes out. But in the bottom line, in terms of, right, you know, sort of openness and exchangeability, there will be great value brought from, you know, sharing files to print, you know, what you want, where you want. And I don't think that, you know, IP will even close to entirely impede that. So in a way, I think, you know, we'll have advancements at both ends of the spectrum. Thank you all again.